Hey there, my name is Noah Tressler, and I'm going to talk about my project that I did, which was on the Euler option. The first problem that I decided to approach was problem number 2. In this problem, I was asked to sum up the even-valued terms within the Fibonacci sequence. And so in order to do that, of course, I had to think about, well, what is the Fibonacci sequence to begin with, and what are the terms in it? And so the first set of pseudocode below, in short, sets a function. The function outputs the Fibonacci numbers, and it takes in sized values. And so we're going to initialize Fibonacci, the first Fibonacci number and the second Fibonacci number to be 1, because we know that the first two terms in the Fibonacci sequence are indeed 1. And so then we'll set our k to be 3 because we want to start with the third value in there, right, that we want to generate. And then we'll send it through a loop. And we'll consider what the algorithm is of the Fibonacci numbers, which of course, right, we take the, let's say that we were talking about the first and the second numbers in the Fibonacci sequence. We would take the first number, add it to the second number, and that would spit out the third number. And so what does that really mean? That's really saying, okay, we'll take the Fibonacci number that's currently at hand, so fib of k minus 1, plus the two Fibonacci numbers ago, add those together, and you're going to spit out the number that you want, fib of k. So Fibonacci number at the third number in the Fibonacci sequence would be the first Fibonacci number plus the second Fibonacci number, right? And that gives 1 plus 1, which is indeed 2, which is obviously definitely going to be the third number in the Fibonacci sequence. And so once we've spit out the Fibonacci sequence, then we can consider summing up the terms, but specifically the even value terms within that, by then running another loop that starts off with, it's going to be a while statement, and then it's going to have a for loop nested within it, and then an if statement within that for loop. And so what we're going to do is we're going to let this val be set to be 4 million, because we know the values do not exceed 4 million in the Fibonacci sequence. That was an assumption that we made from the get-go. And that was in my solution procedure process portion. And so what are we going to do? We're going to say while k is less than the value, or val, right? While k is less than 4 million, because we know that we don't exceed that, we're going to send through an I loop, for I goes from 1 to val. And then we're going to say, okay, well, if the number in the Fibonacci sequence is even, hence fib mod 2, right? Any number divisible by 2 is even, and if it's not divisible by 2, then it cannot be even, right? That is an if and only if statement. If, right, or I should say, don't let me start with if. I should say a number is even if and only if it is divisible by 2, and it can go the backwards way too. A number is divisible by 2 if and only if it is even, right? And so we know what fib mod 2 tells us is that if if we get fib mod 2 to equal 0, that tells us that when we take the Fibonacci number and divide by 2, we have a remainder of 0. If we have a remainder of 0, that tells us that it was indeed divisible by 2, and thus it's even. And so we know that if fib mod 2 is exactly equal to 0, then take the sum and add it to the Fibonacci of that index, and then we'll replace it with sum. And then if it isn't, then we'll just continue to run back through the loop and go on and on and on until we end up reaching our final, or satisfying what we had started with in our while piece. And so that sums up all the even values in the Fibonacci sequence, and that gives us a value of 4,613,732 as a result. One of the interesting things that I found about the Fibonacci sequence, along with many other algorithms, is that there's already a lot of built-in commands within MATLAB to do this. I obviously didn't want to just use that. I wanted to use some of the stuff that we have learned and covered in class, but it's very interesting and kind of cool that this stuff is actually already programmed inside of these programs to just do it. So, people have already done this type of legwork, and there's actually functions and different commands that can be called to just generate these types of things. Here at the top of the screen, you'll see figure 1.1 shows the first 20 values in the Fibonacci numbers, and you can see that they get big, and they get big pretty quickly. And so we can think about how it's kind of cool how this was generated by just using a simple algorithm, honestly. with a function and some loops, and how the computer is really, really awesomely efficient in doing these calculations. It makes life really, really easy and really awesome. The next problem that I chose to look at was problem number 3 from Euler. And this problem asks us to find the largest prime factor of the number 600,851,475,143. And so definitely thanked my computer for this one, because this one definitely is going to want a program and is just begging for a computer to solve it. Because otherwise, your hand and my hand, not going to be feeling so good after about an hour of working on this one. I think we can all agree on that one. So let's think about how we might help use the computer as a crutch here. You can see here on the screen the pseudocode that I wrote to make this happen. But in general, the idea was, if we know that n is greater than 1, if we let that be the while condition, while n is so big, while n is bigger than 1 specifically, for the divisor goes from 2 to n, divisors being, right, divisor is what we divide, the number that we're dividing by. If n mod divisor, right, the number mod divisor, hence, if when I take that n and divide by divisor, I get out a whole number so that the remainder is actually 0, I want to replace n divided by the divisor with factors, right? I want to throw that in factors, add it to the list in layman's terms, and then end the if statement, right? Why do I want to do this? Well, I want to think about what the factors are of my big number that I was given to begin with. If I can think about what my factors are of that, then I can go further and think about what the prime factors are within that list, and then I can find my resultant. And so after I've done that, I will end my if statement, and then I would replace divisor plus 1 with divisor, right, so that I'm continuing to run my loop. And then we notice at the end here, it says to display the factors. And that is simply because I want to now display my list of factors. But once I have these factors, I'm not really done, because I don't know what the factors, how do I know if they're prime? How do I know if they're not? Etc., etc., etc. And so you'll notice here at the top of writing, it says to refer to some lines 46 through 53 and 54 through 58. So I'm actually going to come back to this problem towards the end, because I want to explain what the code on those lines is doing, because it will help to understand how I can then take that list of factors that I've just written and generate out which ones are prime, how to figure out which ones are prime, so that I can answer the question of what the biggest prime factor of that big, huge number they had given me, 600,851,475,143 specifically, was. So we'll come back to this one towards the end. Alrighty, this problem, number 7, asks to find out what the 10,001th prime number in existence is. And so I jumped to this problem, while there are definitely a few other problems that I did between number 3 and problem number 7. I jumped to this one because this one and also the next one are going to be the ones that use the code, or some of the code that I used after I found that list of factors in problem number 3. So we'll talk about that in just a second. But problem number 7, again, we're asked, what is the 10,001th prime number in existence? And so to do this, we'll first need to think about generating, well, really, for this one, we'll need to think about generating the prime numbers between 1 and 10,001. And whatever the 10,001th prime number is in our list is our 10,001th prime number. And so, how might we do this? Well, to get started, I'd like to generalize a bit, because this is obviously a lot going on here. But in short, the main idea of this code is we say, all right, let's start off by generating an array of zeros and ones from 1 to whatever that prime number you want to know is. Let's generate an array of zeros and ones between those two values, where zeros represent numbers that are composite, hence non-prime, and ones represent the numbers that are prime. And so what happens is is that the placement in the array is going to be representing the number specifically. So for example, or excuse, the number that we're looking at. So for example, we need to make the code know that when I look at the 5th place in the array, I'm actually talking about or asking the question of, is 5 prime or composite? If 5 is prime, make it 1 in the array. If 5 is composite, make it 0 in the array. And so to do this, you see some code here, but the use of mods is going to be quite critical because we can think about whether or not we have remainders. And we can use I and j as indexes to vary so that we can look at many different values, right? Because we want to say, okay, is it divisible by 2? Is it divisible by 3? Is it divisible by 4, 5, 6, 7, 8? We have to test all of these things, and we got to test a lot of numbers because in order for a number to be considered prime, it must only be divisible by itself in 1. And so in doing that, we're then going to spit out an array of zeros and ones. And so after we have our array of zeros and ones, we want to consider how we take that array and turn it into the actual numbers we want, because the old idea and goal of this problem was asking us the question of what the 10,001th prime number is. And so to do that, the pseudocode here is going to represent the code that I used to make that happen. But essentially, we basically want to let us set an index that goes from 1 to n, and we think about, okay, well, if x is evaluated at the index is 1, then we want to take the index and add 1 to it and then replace it with index. And then we're going to let p of index replace I, since it's really all about the placements in its original array. Right, because like I said before, it's really looking at what place that 1 is at in the array as to what number it is. It correlates 1, the 5th spot in the array correlates with 5, and it knows that. And so when we call this index in, and we use our we put that IDX into this p, we can for placement we can actually pull out and say, okay, well, this I is in the it's the 25th value this value is 25 values into the array, so therefore it must be representing 25, and 25 being represented by a 0, and we just said at the top of the pseudocode we don't want any values that are represented by 0, so do not include 25 in that final list of primes. And so obviously 25 is not a prime number, so woohoo, great, 25 is not in my list of primes, and we're good to go, which is exactly what we want. And so down here in figure 1.9, you see that I have put in that array of zeros and ones. And then in figure 1.10, you'll see that I've then run it through my second piece of code so that it's then spit out the actual values right towards the end there. And so we see that 9,973 is indeed the 10,001th prime number, which is displayed then over here. The next problem was problem number 10, but before I do that, I just want to kind of go back to that problem number 3 for a moment. So how does this apply in number 3? So let's go back, and I'll just show this list, or this table, as what I've outputted here. And so this applies here, this primes code applies here, because once I've displayed factors, then I can look at that last factor, the biggest factor in my array of factors, which in this smaller example I have in figure 1.2, it was 250. Because I wanted to do, basically in this example in the paper, I said, okay, 500. I want to know what the biggest prime factor of 500 is. And so here I've displayed all the factors, right, of 500. And that's awesome. But then I want to say, okay, I know that the biggest factor is 250. So if I'm trying to find the biggest prime factor, then I can go back to I can go to number 7, that set of code I had talked about there, in lines 48 through 53. I can look at that code and say, all right, I want to generate the array of zeros and ones between the list of primes between 1 and 250 with my array of zeros and ones. right? And so my ones represent primes and my zeros represent non-primes. And so then, after I've done that, then I can say, okay, that list is all the prime numbers between 1 and 250. And so then I can take that code and I can use my set of code from lines 53 to 58 that then turns those zeros and ones to the proper values, or excuse me, really the ones to the actual values that they are. I can use that code and do that, and then I can say, okay, well, what is the biggest value in this list that is also a factor of 250, or excuse me, of 500? And when we do that comparison using a smaller scale here, we get the answer to be 5. So the biggest prime number of 500 was 5. In problem number 10, we're asked, what is the sum of all the prime numbers below 2 million? And so this one's actually very easy because we've already written code that will do something for this very, very quickly. And the code is the one that we just talked about. We want to know the sum of all the prime numbers below 2 million. And so what do we have to do? We just have to let the list of zeros and ones, we'll have to start that off and go from 1 to 2 million. And then we're going to take the next set of code and convert it, right? We'll convert it to the actual numbers that we have at hand. And then we're just going to sum up that set of values. In this figure here, I've demonstrated plugging in that big number. But we have a problem, and that is, unfortunately, we can only represent, right, but such a big number in MATLAB. And so, because of our bit sizes that we've talked about. And so we would have to use another programming language that has bigger bit sizes in order to actually represent this. But this would be the way that we would go about coding this up. Problem number 20 asks a very interesting question that actually was something I had never really considered, and it was something that I really had to think outside of the box for, and it was, how do we take the value that is output from evaluating 100 factorial and sum up all the digits of its result? So, if we think about what 5 factorial equals, right, that would be 5 times 4 times 3 times 2 times 1, which is 120. And so if we think about what the sum of the digits in 120 is, that would just be 1 plus 2 plus 0, which is 3. And so we're trying to do this on a much larger scale. And so we have to figure out a way to write code so that it can actually go through and look at each digit within the value itself. The first thing we're going to want to do, though, is actually write code to compute compute a factorial. And so that's what 59 through 61 here represents. It says for I goes from 1 to n, in step sizes of 1. Replace factorial with factorial multiplied to the index, and then we'll end the for loop. Very, very simple code there. So once we've spit out the actual resultant from the factorial, we want to say, okay, how do we sum up the digits? And so here in the code through 62 through 66, you'll see how I went about doing that. And essentially the idea here is that I'll introduce a while loop for when val is greater than 0. And then I'll use the idea of k replacing val mod 10. This actually becomes a really good method if you introduce a floor command that rounds it off pretty well. And you can do some more research about that, but this definitely, through my research, seems to work pretty well. However, we do have a big problem in actually computing this Euler problem, and it goes back to the idea of bit sizes. So here on the screen in figure 2.3, you see the computer spitting out the value of 5 factorial. It's 120, awesome. So great, we would sum it up and it would work out. And so we could certainly input that figure if we wanted to, but instead I decided to talk a little bit more about why I didn't put in the sum of 100 factorial. And that is 100 factorial can't actually be represented on the computer because it is so big. To give you an idea, I have inputted a picture, which is now displayed on the screen, figure 2.4. Just to show how long 100 factorial is, and it is huge. And so we can definitely see that MATLAB is not going to be able to represent a number that size. So summing up all of its digits would be, right, impossible in MATLAB. We could certainly use another programming language to generate this, but MATLAB is not going to suffice here, unfortunately. Going to problem number 4 now. In this Euler problem, I essentially was asked to find the biggest palindrome prime number out there. And so in order to do this, we need to know what a palindrome prime number was, and that is simply a prime number that can be written both the backwards and forwards in the same exact way. For example, 1001. 1001 written from left to right is going to be exactly the same value as written from right to left. And so to figure this out using a computer program is going to be critical. And I'll let you read through the pseudocode a little bit, but the general idea to do something like this that you'll have to consider is all about strings, because we needed to, in using a number 2 string, specifically here is what I believe I used. And the reason is that we have to look at each individual value in the number, right? Because in order to determine if it is palindrome prime, the number order is critical, right? We need to think about, are the numbers the same going forwards as they are going backwards? And so that was the idea here. And then we're talking about the length and replacing it with len. And that first set of code, 20 through 24, was actually establishing whether or not it is palindrome prime. And so does 25 through 28. All that code together helps us to see if a number is palindrome prime. So you could actually plug in what you're going to see in table 1.2. You can actually plug in values within this code, and you could say, okay, is 1001 a palindrome prime? And it will say to you logical no, logical equals 0, or logical equals 1, which is exactly what I have in table 1.2. And so this code that I've written so far that we've seen, 20 through 28, give or take, is essentially establishing whether or not, or maybe I should say palindrome primidity of the number. Is it palindrome prime or is it not palindrome prime? But here the Euler problem asks us to then, after we, explain or to, help the computer realize what a palindrome prime number is, we need to figure out what the biggest one is. And so to do something like that, we need to set 2 big indexes, I and j, let them go from 100 to 999, and let I be multiplied 2j to replace n, and we continue to go through our code here, our pseudocode there, and we'll see how we would finally go about finishing that up. I want to talk a little bit about this table that I have here. You'll see that I have simply inputted values of n, so say 111 and a few others, which I'll show in just a moment, and then we prove it by plugging it into the program. And so when we do 111, you can look at 111 and tell it's a palindrome prime, right? And so it's clearly spitting out logical of 1, telling us it's true. And so yeah, that's a palindrome prime. If we take a look over here at this part of the table, right, we plug in 300, it's clear, our intuitive guess is that it's not a palindrome prime. And of course, the computer tells us it is certainly not a palindrome prime. 1500, right, we can look at that and tell that is not the same number backwards and forwards, right? So it's obviously intuitively not a palindrome prime, and of course we see that the computer tells us that exact result. And 3003, it looks like it's palindrome prime the way it's written, so let's test it and see if it is palindrome prime, and of course the computer tells us that it is. So if we go back to the overlying question, what is the largest palindrome prime? It is 906,609, and this right here was the computer. Figure 1.5 is the computer outputting that value within it. The last question I worked on was the question of determining what the sum of the natural numbers between 1 and 100 squared subtracted from the value of each one of those individual natural numbers squared gave. And so do this, I started by initializing a temp variable, sum, right? Just some sum. And we set it to 0, initializing it. And then we're going to want to start a for loop and let it go through an index from 1 to 100. And then we'll take sum and add it to the index, and then it will continue to add these it'll continue to add each as it goes through the index, it's going to continue to throw on whatever that sum was at that value. It'll put it into sum. But all we're doing right here is just taking and adding up all the natural numbers between 1 and 100. After that, you'll see right here at line 40, we want to take that sum and square it. And so we then took the sum and squared it, and we replaced it with sum squared, or sum skew, if you will. So that spits out the sum of all the natural numbers, right? So you're thinking something like this, right? 1, 2, 3, all the way up to n squared, right? That's what that first set of pseudocode does there. This next piece of pseudocode is going to take and spit out this idea. And I should have had these all added together. So this is going to do something like this. Right? That's what this next piece does. And so the only real difference that's going to be happening here is that instead of adding on I, like we did here, our index, we're going to take and we're going to square that index. And in doing that, we then can then take stored sum at the very end and replace it with this different, slightly different variable name. That way we can differentiate between which one is the sum of all the natural numbers between 1 and some number n squared versus what is the actual sum of the natural numbers between 1 and 100, each individually squared. Once we have those two resultants, we can then take this sum skew and subtract sum squared, and then we'll get the value at hand. In this question specifically for Euler, they are asking us to figure out what the difference is between the natural numbers between 1 and 100 added together and then squared, and the natural numbers between 1 and 100 added together being squared each go round. And so when we do that, we find that, or we result these values that you see here in the table 1.3. Figure 1.6 represents what we get out when we take all the natural numbers between 1 and 100 and add them together and then square them. That number's pretty big. It looks like it's 25,502,500. And then we see that when we take all the natural numbers between 1 and 100 and square them each go round and add them together, we spit out 338,350. And then figure 1.8 shows the difference between those two values. And so to answer the question here, we get out 25,164,150 for the difference between the sum of the natural numbers between 1 and 100 squared subtracted by the natural numbers between 1 and 100 squared each time. And that would be how we would go about doing something like that. Overall, I gotta say, this man right here in this picture, Euler, has had some awesome questions and had some awesome impacts. And going through this project, you really get to see kind of how impeccable the computer is at representing so many things on it. It's truly amazing. And it will be a miracle to see where the world goes and how much more is coming in the world of computers that we don't even know about yet. And maybe could even look back on this video or this code or anybody's in this class in 20 years and say, wow, that's so outdated compared to, what we had just X amount of years ago. I mean, shoot, if you think about just how, bit sizes has changed over the past several years, how we can now represent bigger and bigger numbers, and we're getting to represent more and more and more, and we're starting to see things that we never even knew about mathematics, right? Within bifurcation diagrams or things like that make you go, wow, there's some really awesome things going on out there in this world that we don't necessarily even know a lot about yet. So, and it's all because of the computer and programs and things like that. So Really awesome, and this is definitely an eye-opener to all of the things that are out there.